started. Uh, so welcome to the sixth problem solving session of this course. Uh, I think everything is working fine. So this is a new setup for me. If at any point you're not able to hear me or see the screen, then please let me know. So we are going to discuss the problems of week 6 today. Specifically the problems that were given as exercises or assignments in the previous offering of this course. So let's go to the whiteboard. Okay, so in this week we have seen videos, we have watched videos which dealt on this topic of Treewidth. So we have seen this topic of Treewidth even before. This week there was a continuation on Treewidth. So to recapitulate, just a second. I think to recapitulate, it would be good if we look at what we discussed last time. So we'll take a look at it. Yeah, so we defined what is a tree decomposition for a graph, and we looked at some examples for some graphs, and then we tried to get a tree decomposition where the width of the decomposition is minimized. So we defined what is tree width.
So can you repeat this definition, the definition which you wrote here? I mean, about the tree decomposition. Yeah, this one. These 2 points.
Okay. So we said that a tree decomposition of a graph is decomposing the graph into a tree such that two properties are satisfied. And the properties were that for every edge in the graph, we wanted to have some node in the tree decomposition that contains both the endpoints of that edge. For example, this is an edge F. So there should be a node in the tree decomposition where both H and F are contained in one bag or node. So for example, this is one node where we have F, G, and H. So both H and F are present. This is the first property, and this property should be true for every edge of the graph.
And we can have this edge in many more bags. So it is not necessary that it should be present only in one bag.
That is correct. It can be
Okay.
present in multiple bags.
Fine.
And we also want to ensure another property. So for every vertex in the original graph, we look at, for example, let's say we look at the vertex B. So all the bags that contain B, we wanted that these bags are in a connected component. They form a connected component. So that was the two properties that we desired in a tree decomposition of a graph. And then we said that, okay, how do you decide which decomposition is good, which decomposition is not so good? So we said that if you consider there is only one bag that contains all the vertices, that is also a valid tree decomposition. But what we desired was a tree decomposition where the bag sizes were comparatively small. So we said that the size of the largest bag minus 1 is the tree width of a decomposition. And then we tried to see what is the tree width of different kinds of graphs. And there were multiple statements for which we decided the correctness. We found out the correctness of those statements or falseness. Specifically, we saw that for a complete graph on n vertices, the tree width was n minus 1. For forests, the tree width was 1. For cycles, the tree width was 2. And we solved a couple of examples on the same lines. For a complete bipartite graph, we saw that the tree width is the minimum bipartition size of the two partitions. And there were a couple of statements for which we decided whether they were true or false. Fine. So in this session, we will not need, I shouldn't say need, we will need these definitions plus some other definitions. So we will go back to a new whiteboard. Okay. So in this session, we will define some more terms. For example, we will look at something called a nice tree decomposition. So at the outset, I would like to emphasize that uh, this nice tree decomposition definition is designed such that it helps us in designing efficient algorithms for different problems. So far we have seen that, okay, we want to minimize, we want to find a tree width where the maximum bag size is sort of minimized. So here we are looking at designing or constructing tree decompositions which have certain properties which we call the nice properties. So a tree decomposition, or rather a rooted tree decomposition, rooted tree decomposition means in the tree decomposition one of the bags will be called the root, and then it will have children. So there will be a well-defined parent-child relationship and a well-defined ancestor-successor relationship. So a rooted tree decomposition is called nice. Nice. Okay. If the following properties or conditions are satisfied. So we have to satisfy. Okay. So and suppose that the root is denoted by R. So the root node is denoted by R. So what is the first condition? The first condition is that the bag corresponding to the root is empty. So X sub R denotes the set of vertices in the bag corresponding to the root R. So X sub R is empty and X sub L is also empty. That means for every leaf, for every leaf in the tree decomposition, the bags are empty. So I will say that it rooted tree decomposition T. So I will add this. So we're denoting by T the rooted tree decomposition of a graph. So this is like, these are, let us say this is one of the tree decomposition. So I'm saying that, okay, this is the root and in the root there is nothing. This is empty. Some vertices are there, but in the leaves also there is nothing. Okay, so that is one property that we are willing to ensure. And the second property is that every non-leaf node, so we have characterized the root node and the leaf nodes. So non-leaf nodes, that means the internal nodes other than the root, every non-leaf node of the tree decomposition T is one of the following types. So we will characterize the non-leaf nodes into three types. The first one is an introduced node. The second one is a forget node. And the third one is a join node. Yes, I will pictorially represent what these types are. Of course, you can look at the book and look up the formal definitions. So a node means a bag. So in the tree decomposition, let us say this is a bag. So it has certain vertices. I don't know. Let us say ABCD, whatever. So we denote this node by T, and of course xt denotes the set of vertices in the bag. So for example, in this case, xt is ABCD. So ABCD are original vertices in the graph G. So if T is the, so let us say the graph that we are interested in, the graph for which we are finding the tree decomposition is denoted by G. So ABCDs are some vertices in G, and we will call a bag in the tree decomposition as an introduced node if it has a single child T dash, and by x sub T dash we denote the set of vertices in T dash. So x sub T dash, let us say, is ABC. So you can see that if this is the case, that means that what is the difference between the bag contents of T and T dash? There is only one new vertex which has been introduced in the bag. So earlier the bag was ABCD. So just let me write ABC here. So now this bag has ABC. So one vertex D is introduced in the parent T. So there was a child T dash, which is the, sorry, there was only one child T dash of T, and T has vertex other than the vertices of its child. That means this vertex T is introduced at T. Then we will say that okay, T is an introduced node, and in this case, the vertex T is introduced at node T. Okay. Okay. So I hope this is clear. Okay, so let us move to the definition of what is a forget node. So a forget node, let me take a different color. So let us say there is a bag T, and this is corresponding to let us say some vertices, let us say ABC. So xt, the content of the bag T is A, B, and C, and it has one child, a single child, which is T dash, and let us say T dash is A, B, C, and D. So I'm just taking some example. So A, B, C, and D. So that means the node T is such that the node T is such that the vertex D, exactly one vertex D, is not present in this node T. So this vertex T is forgotten in this node T, and that is why we will say that this node is a forget node. Okay, so let me write it. So we will say that the vertex D is forgotten at node T. So there is exactly one vertex, which is a difference, and that vertex is missing in the parent. In that case, the parent will say is a forget node. Okay, it's just symmetrical definition. Okay, so let's move to the definition of what is a join node. Okay, so let us take a different color. So we are going to define what is a join node. So join node, so it's a bag, let us say T, and it has some contents, xt, some set of vertices. It has exactly two children. T1 and T2, and they have exactly the same content as their parent. So in that case, we will say that T is a joiner. Okay.
So in case of the introduce node, introduction node, what is the right name? Introduce name or introduce node or introduction node?
Introduce. So the book
Introduce.
says yes.
Yes. So yeah. So D has been introduced on the node T, and which is not there in T dash. So can D appear somewhere else in the tree?
Yes. It can
Okay.
appear somewhere else in the tree as well.
Fine.
So whenever
And
whenever it is getting introduced, you say that okay, this is an introduced node.
fine. And can this node T have more than one child?
No. So the definition is that exactly one child should be there.
All right, all right. And can you please repeat the definition of the join node? So I understood it like say the cardinality of the I mean all the elements of the parent are there in both the child I mean both the children.
Yes,
So is this necessary that the node T has exact two children or can it have more than
exactly
two
two
children?
children. It should have
Okay,
exactly two children, T1 and T2, and the content of the bags should be same.
right, right, clear.
Okay, so such a decomposition. So so nice decomposition has these properties that the root should be empty, the leaf should be empty, and internal node should be like these. That there is a basic idea is that whenever you are looking at a parent-child relationship, you are looking at identical bags or bags that differ by at most one vertex. So that is going to help us in designing algorithms.
Yes, and what about the number of the vertices in the tree? So since we have since root is not containing any element, and moreover leaves are also not containing element, so clearly the number of the vertices in the graph and the tree cannot be same, because had there been a connectivity among the vertices, so those vertices cannot, I mean, that vertex cannot become the root in the tree because it has to be empty.
Correct. So the number of vertices in the original graph and the tree decomposition need not be same. In fact, we will see in the next example that they can differ. So if the question is what is the relationship, then uh, I don't know whether there exists a relationship between the number of vertices in the original graph and the number of bags in the nice tree decomposition, but uh, there might be some relationship, but I cannot answer that for sure.
Okay, 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 fine, fine. But then the number of the vertices could be different. Rather,
Yes,
should
yes,
be
that
different. Yeah.
yes, that we'll see now. That they, definitely they would be different. Yes.
Yes, fine.
So question to understand this question, whatever definition of nice decomposition I give will be useful. In fact, without the definition of nice tree decomposition, we won't be able to solve this question. So I'll give a minute or so to read this question.
Okay.
Okay, so we have been given a graph. In this graph, there are five nodes, sorry, vertices. So for a graph, we'll say vertices, and for the vertices in a tree decomposition, we will say nodes. So in this original graph, there are five vertices, and this is a valid tree decomposition with tree width 2. Okay, so we are interested in finding the maximum size of an independent set in this graph. Okay, so to find the maximum independent set in this graph, we have seen an algorithm in this lecture video, and this algorithm is a dynamic programming algorithm, and it computes certain table entries. The table is denoted as small m, and in this question they are asking that they have given certain table entries and certain table entries are missing. So we want to fill these missing table entries. Okay. So the first thing we have to do is we have to convert this. I mean, not convert. I should say that first thing is we have to find a nice tree decomposition of this graph. And fortunately, we have been given this nice tree decomposition. Now, first, let us verify that this is a nice tree decomposition. Okay, so you will be asked the first question that might come to your mind is that why is the root non-empty? So I think that by definition, the root should be empty. And that is in the book they have given. And as you can see, the leaf is also having one node, so leaf should also be empty. Uh, but without loss of generality, they did not show the empty leaves and the empty root. But you can always, append one empty bag here and an edge from the empty bag to this node.
So does it solve any purpose, this empty thing? That the root should be empty or the all the leaves should be empty?
Mm, So in the dynamic program, if we see, then in this dynamic program, the base cases at the leaves, they have just added the value 0, 1. So first we have to first I will define in a minute or so that what is the definition of every table entry. So what does this m of x1 comma e comma h what all these things mean, and then we will be able to answer your question that whether having empty leaves and empty root serve any purpose.
Okay, okay, fine.
Okay, so uh, so for our purposes, these are all internal non-leaf nodes because the empty root node and the empty leaf nodes are not shown. So for every non-leaf node, the condition that we have to see is that whether every node can be categorized as an introduced node, a forget node, or a join node. So what shall we categorize the root node as?
So this one is a joint node.
Correct. So because both its children are having identical back content, so this one is a join node. So how about x1?
This is introduced node. This is introduced node and this is introducing E.
Correct. So as we can see, these two are introduced nodes. This one is also introduced node, introducing C. This one is a forget node because it
Yes,
is, yes,
it is forgetting F. Yeah.
correct. So here E is getting introduced, and interestingly, here also E is getting introduced. So the question that you asked initially, that whether a vertex can be introduced twice, here is an example.
Yes.
Okay, so we can verify that every node can be categorized as either introduce or join or forget. So this is a valid nice tree decomposition of the given graph. And once we have this decomposition, so this is a small graph. In fact, uh, there are techniques in which one can find nice tree decompositions, and I think those are discussed in the lecture videos also. But for the purpose of our question, we won't worry about how this tree decomposition, nice tree decomposition has been computed. We have been given this, and we'll see. Uh, so the next step is to understand that what these entries in the two-dimensional array or table M mean. Okay, and then once we understand the definition of these entries, then we will be able to argue that what these missing trivial entries should be.
Yes.
Okay, so let me define what these things are. So you are not able to see the upper part of the board, I believe.
Yes. Now, right now, the entire screen is blank. Nothing is visible.
Okay,
It's all blank. Yeah.
so I added two tick marks. Is it visible to you?
No, no. It yes, it is. It is somewhat. I mean, to the upper side, upper corner, and I could not see it completely. It is visible now. Yes, it is perfectly visible.
Okay, so you're not able to see at least 20% of the board. So I'll just write on the bottom 80%. Okay, so okay, let me define what it means. So a table entry, uh, just a second, I'll just quote from the book. Mx comma s is a table entry. So this means the maximum possible, or so we are in the unweighted setting. I'll not say weight, so just say that maximum independent set S cap such that S is a subset of S cap, and this is a subset of, so they are saying Bx. I'll just say Bx. So in the book it is saying Vt, but fine. I'll just check the question once again what they're saying. Okay, this is already written in the question. So they're saying that Mx comma S means the maximum size of an independent set I, which is a subset of Vx. So Vx means the uh, set of vertices that appear in the subtree rooted at x. So for example, the v of x1 is nothing but all the vertices that are contained in the bags which are in the subtree rooted at x. So for in this case, the value of v sub x1 will be c, e, h, and a. So these are all the vertices that are lying in these bags. Okay, so the definition of Mx comma S is the maximum size of an independent set I among these vertices that are rooted at this. Let us say that we are looking at x. So suppose we set x is equal to x1. So we want to know what is m of. So we're just going to do it pictorially. So what is m x1? Let us say c. Okay. So what is s? S is any subset uh, of the elements in x1. So here, any subset S of its bag Vx. So for a node X, they're denoting the bag as V sub X. So what is the bag content of X1?
So back content of X1 is ACEH.
Right. So CEH, how many subsets are there of CEH?
How many subset of the CH? So there could be eight subsets possible.
Yes. So you see there are 8 entries corresponding to X1. So X1 5 is one entry, X1 singletons 3 entries, cardinality 2 subsets 3 entries, and cardinality 3 one subset. So for every node and every subset of the contents of that node of the bag, there is one table entry, right? So what is the table entry denoting? So this table entry is nothing but the maximum size of an independent set of the vertices in Vx, that means of the vertices that are here in the subtree rooted at x1. So CH and A. Okay. And with the additional property that this independent set intersection with the contents of the bag is exactly S. So it is slightly tricky. So you can take a minute or so to let the definition sink in. Then we will make the computations.
So when we computed this value ACEH, so this is the value of what? This is the value of V of X.
So you
Like say
said,
here, what is the value of V of X1? So what this ACEH is?
okay, so Vx denotes the set of vertices that appear in the subtree rooted at X. So let us write down for clarity. So let us say we want to find Vx1. So first thing
Yes.
is, what are the bags rooted at x1? I mean, in the subtree rooted at x1, these are the bags. Now, what are the contents of these bags? C, E, H, and anything else? A is
A.
there.
Yes.
So therefore, this is the definition. By definition, this is the value of V sub x1.
Yes.
So we are looking for that maximum independent set of these four vertices in the original graph. Okay, so the original graph should be in the. You're not able to see the original graph. I will try to copy this here. Just give me a minute. We'll copy the original graph. I have to paste it somewhere. Let me delete this. So you're able to see the original graph now.
Yes. Yes. Visible.
So we want to find. So when we're looking at this entry, so basically we are asking that what is the maximum independent size for this set of vertices C, E, H, and A such that in the original graph. So let me mark C, E, H, and A. So what is the maximum subset of these four vertices in the original graph that forms an independent set? At the same time, the intersection of the independent set with the box or the bag CH is exactly C. So we are asking that question when we are writing this table entry. Okay.
Okay. Okay.
So this is already uh,
Yes. So
in.
since its value should be equals to S, and the cardinality of the S here is equal to 1. So out of these 8 entries, we will focus only on those entries whose result is 1. Then only this condition will get satisfied.
Okay, so let us not worry about this particular entry. I just wanted to uh, give you an understanding of what is the meaning of every entry. So this is not the entire description of the entries. So as you can see that there are some values which are set to minus infinity. So we have to also define that for what table entries we are setting the value to minus infinity. So let me define that first before we move forward. So this is part of the video, but I'll just write it here. So I'll just write it here. So if no such independent set exists, so independent, no such independent set means the kind of independent set that we are looking for, and if such a set does not exist for an entry x comma s is some subset, then we will set this entry to minus infinity. So that means, so basically there is no independent set of that. We should say that okay, independent set size is zero, but by convention we are saying that okay, independent size set size is minus infinity. This is just by convention. Okay, now what will be a more prudent way to look at computing these entries would be to start from the leaves. Okay, so let us start from the leaves because they have, you know, uh, their children are empty nodes or a leaf. So these are not leaf nodes. The leaf node should be having empty bags. Uh, Correct. So what is let us look at. Okay, so these values are already given to us, but still let us verify that these values are correct. So what is this m x5 comma 5? Why is this entry x5 comma 5 is 0?
So uh, so the value of the Vx5 is equal to h only, and
Correct.
now we find the independent set containing this element, maximum size of the independent set containing only this element h. So the maximum number of the independent, I mean, such a set would also comprised of only one element, that is h only.
Yes.
So if I take the intersection of h with phi, then
Yes.
clearly phi would be, I mean, if I take nothing is there, nothing is common.
Correct.
Uh, but does it satisfy this condition that the I intersection B of x is equal to S? So here
Yes.
I is equal to H and B of x is equal to H. And what is S here? S is equal to phi.
5.
So if I take the intersection of I and then S, so I get phi in return. Yes.
Correct.
Yeah.
You are right. So we have understood, of which I'll just write down. So the bag of X is H, and there is an independent set which is H, but then I intersection the box bag of X is also becoming uh, H. Then we don't want that. Therefore, we cannot say it is 1. So therefore, the independent set itself is 5. So 5 will satisfy this. So now this will become 5, like you have explained. So that is the reason we have an empty independent set, and that is the reason x5 comma 5 is 0. So that is the base. Now x5 comma h. So when s is equal to the set comprising of h, that is 1, and that is by the same argument that okay, h itself is an independent set. H itself is an independent set, and if you consider the intersection of h with s in this case is h, then we are getting uh, sorry, if you consider this independent set H with the bag content, which is H, then you get S, and that is what is expected. So that is the maximum independent set containing H only. So similarly, they have found all these values, but in between, so so like we have already said that some of the nodes are join nodes, some of the nodes are introduced nodes, and some of the nodes are uh, remove or forget nodes. So
Yes.
for each of these nodes, there is a specific rule applying which will compute the entries bottom up. So bottom two elements, or rather bottom two entries are taken care of. Now we will compute entries towards the top side of the rooted tree. And to do that, let me first define that what are the different recursion rules for computing the entries for introduce node, uh, forget node, and join node. So this is in the book. Maybe I'll just write it within this visible area only. So I'll just write in shorthand. These are the options. So I'll just push the options to the side. Right. So for introduce node, the book says that follow this recursion formula. So for an entry m x comma uh, bag of so you're saying s, this option is denoted by s. So if x is an introduced node, so x is an introduced node. So x is an introduced node. So in that case, the bag entry corresponding to m of x comma s is equal to m of x dash. So x dash is a child of x. Okay, so I'll just write it. So x dash I'll just draw. So x is this, x dash is the child of x, and if that is the case, and we already have the entry corresponding to the child, then we will set it to this. If the introduced node, so let us denote the introduced node by v. Let us say that so x is an introduced node. So let us say the vertex which is introduced by x is v. So v is the introduced vertex. So this is slightly tricky, but this is the description of the algorithm. I can't help it. So if v is not part of the uh, parameter in the table, that means it is not part of this subset of the bag which we are interested in, then we will just set it to the same value that in the child node, that is x dash. Otherwise, if v is indeed part of the subset, then we set it to the value at the child node minus v plus 1. Okay, so what does this mean? So let me take one of in this figure only. We'll apply this formula. So where can we apply it? Right. So the first missing thing is this. So the first thing that we want to compute is the value of this table at x2. Uh, so it is written as c comma h, but it is actually this is actually a set c comma h set. There is a typo. Basically, as you can see, basically we are interested in computing this entry. Okay, so ch is an introduced node. So we're interested. So we're interested in computing the entry in the table corresponding to this node, which happens to be an introduced node, which is introducing c. Okay.
Yes.
So right.
So yes, so for x2, the b of x2 is equal to ACH, and
Exactly.
yeah, so it is ACH. The b of x2 is equal to ACH,
Right.
and now we find the yes. So we have been given x2. So yes, so the I here is the independent set of the vertices x2. So can I see the graph? I will note down the graph now so that I find the value of I for the x2. So this is A and then H and F and E and then C. So now in this graph for the ACH, A, C and H, so the number of the vertices which are not connected. So how to find the independent set of the, uh, so here the independent set comprises of only its value is 1. So there are two vertices A and C and which are not connected. So the value of I is equal to AC. And so since I is equal to AC, and now we need to take the intersection, its intersection with CH. So for the CH, four possibilities may arise. So if I consider one possibility, the intersection of AC and C, so this value comes out to be, so what this value, I mean, what do we want that if I take the intersection of AC with C, so clearly this value is C. So its value would be 1 watt or 1. Fine. And if I consider only H, then its value would be 5. And but then if I consider both C and S, then also its value would be 1. But following this rule, since CH is an introduction rule and C is being introduced, so following this formula, since C is not the part of C, in fact, is the part of this CH. So therefore, we go for the second formula, that is the M of the X3 and M of X3 comma H. So plus 1. So then we can refer the M of X3 comma H plus 1, and this value must have been computed earlier. The M of X3 comma H plus 1. So 1 plus 1 is equal to 2.
Correct. So yeah. So I mean, yeah, if you follow the rule, this is the recursive formula. If you follow the recursive formula, then you will be able to reduce this into this. So now this entry is the entry corresponding to the child, and that is already given to us. So the entry corresponding to x3 and h is already given to be 1, and by the calculation which you have already given, the entry corresponding to x2 and c comma h is 1 plus this, because the vertex which is introduced at this node is h, and h is part of that subset which we are interested in, ch. So this rule is applicable and not the first rule. So that is how it's
But
completed.
yeah, I have a doubt here that it's true that by using this formula we got this value as 2, but if we go by the definition, then how will we compute this value as 2? The definition which is given above in the problem formulation, that how do we compute the value of M of X comma S?
So the way this bottom-up recursion, I mean, dynamic programming table filling works is that the definition is just to uh, express to you what every entry means, but the computation have to be bottom up, and therefore there are base cases, and for the base cases you already know the values, and for the intermediate cases you will make use of the already computed values, and you will not directly be able to compute the value corresponding to an internal node from the definition, so you have to go bottom up, and that is the way to go.
But then we have been given graph and we have been given the definition also. So why can't we compute it like the definition which is given in this question? Can you please show that definition again, which is given above? Slightly, if you can slightly scroll it down. Yes, this one, which says that this is the maximum size of an independent set. So here the what is the independent set? Since the value of v of x is equal to independent set, since v of x here is equal to a and then c, ACH. So what
Yes,
is the ACH? Yes. So
a
what is
and
the
c, a
and
and
A?
c.
Yes. So is this value 2 or is this value 1? The maximum independence.
It's two only, a and c.
A and C. Yes. So its value is 2.
Correct.
And if we take its intersection with the B of X, and here B of X comprises of uh, yes,
ACH.
ACH. So
Yes,
if I take the intersection of AC with AC and then H, then I get this, and it should be equals to S. And yes, so this value comes out to be A and C only. So yes, so but then we require this S here, and what is S here? The S here was C comma
CH.
H. So if I take, but then I'm not getting this value as C comma H.
You
The
can also
intersection.
consider C comma H as an independent set.
I see. Yes, yes. That's right. That's right. So instead of taking SC, we could have taken say CH, and then if we take the intersection of CH with ACH, and we got this value as CH. So that is how this value came out to be 2 probably.
So the point is the definition is sort of how the algorithm designer came up with this dynamic programming idea. So that so as you can see that this meaning of this thing is saying that okay, I want you to find an independent set within this subtree only, okay, and I want you to find an independent set containing C and H. So you are finding an independent set containing C and H, and you don't want anything other than C and H also. So what is the maximum size independent set you can get? So you can get other, I mean, so other than CNH, you can get other vertices in the independent set, but they should not be within the bag of X2. That is what it's saying. So I probably am not being able to give the intuition as clearly I should have been. It should have been possible. Uh, but mechanically speaking, if you follow this introduce node formula, then you will be always able to find an independent set of maximum size.
Yes. So what do I observe here? That all the values are either 1 if the cardinality of the S, I mean, all the values are equals to the cardinality of the S. If it is CH, the value is 2. If it is only one element, H, then the value is 1. Otherwise, this value is minus infinite. Yes, and here we have x1 comma e as 2 and y so. If we go as per the definition, then
So
uh,
the definition is saying that you are supposed to find an independent set in the subtree rooted at x1. So x1 is this. So you're
yes,
supposed to find an independent set among the vertices C, E, H, and A.
yes.
So now you're able to see the graph C, E, H, and A. So there is an independent set of size 2, which is A and E,
A
right?
and E, yes. A and E,
Yes. A
yes,
and E.
yes.
So you want E. E definitely you want, but you do not want anything from the back. That means C and H you don't want. But outside of the bag, there is A, so A can be taken. That is the reason this is 2.
No, but according to the definition, yes. So the independent set is what? Independent set here is if I take, so E is mandatory to be taken. So
A
if
is
I
to be
take
taken.
A,
Yes.
A and E, so if I take the Cartesian, the intersection of A and E with E, then the value comes out to be E. And since the size of the independent set is 2, so therefore the value came out to be 2. Yes, it is. It is. I think that yeah, and it's clear from this definition that we want what we want the. So this value will give us the cardinality of the independent set, uh, independent set over the V of the X, right?
Yes.
And such that its intersection with the subset S, uh, I mean, nothing should be common in what being the V of X, in what being the the independent set of the V of X and the S except S.
You are not
So
in. You are not involving the BX. So BX is the bag corresponding to the node. So I hope that you're able to see. So they're saying that the independent set and the bag should intersect such that the intersection is exactly S. So in this case, the bag is CEH. So B of X is CH, and the independent set is A comma E. So they are intersecting at E only. So the E is the intersection. Okay, and that is the reason the definition is true, but the value comes out to be 2. So just look at this expression.
Yes, 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 yes. Yes. Now I got this point. Yes, yes. So yes. So yeah. Yes, fine. Yes, so nothing. Nothing simple can be can be concluded actually. So there is no other option except computing. So the definition is slightly tricky. So no other option except using these formulas and then finally get the value. Yeah, right.
Correct. So for this first question, that what is the value corresponding to the node x2 and ch, we have computed that it is 2. That means there is an independent set for the vertices corresponding to the subtree rooted at x2, and of course satisfying the conditions given of size 2. And we computed this by applying the recursion formula for an introduced node, because in this case x2 is an introduced node introducing h. So now we have to compute three more things. Sorry, four more things. X1 is another introduced node.
Yes,
Y2 is target node. Y1 is an introduced node, and R is the root, which is a join node. So basically, we have to understand what is the recursion rule for a forget node and what is the recursion rule for a join node. And so it is 7 o'clock. Let us come back after 5 minutes
yeah,
and we
sure.
will look at these. And then there are two more questions. So because the question itself is slightly trickier, it has taken a long time, but that is fine because the idea is to understand how the recursion is working.
Yes, sure.
All So, uh, so we have found, if I'm audible, yes. So we have found how we calculate this entry. Uh, but Shivang has a doubt, so I'll explain it once again. Shivang, you are able to see the screen, right? Hello, Shivang, can you hear me? Okay, so fine. So let me re-describe that how this entry x2 c comma h has been computed. So somebody has given this nice tree decomposition of this graph, and given this nice tree decomposition, somebody has found this nice recursion rules. And if you follow these recursion rules, then you will be able to fill all these table entries. And at the end, the table entry corresponding to root and phi will be the maximum independent set size that we have seen in the videos. So the way to compute these table entries is to go bottom up. So first you look at the leaf nodes and then you look at their parents. So basically leaf nodes are empty nodes which we are not showing. So from the empty nodes we are looking at their parents, so which are these, and then everything else are internal nodes. Then we will just follow the child to parent nodes, all this, and then all these table entries will be computed. So you are fine so far, Shivam, right? So if somebody has to do this, then they have to start bottom up. And in this exercise, some of the table entries are left blank. Some of the table entries are question marked. So we want to find these table entries. Okay. So now to find one table entry, first thing we do is to decide what kind of node it is. And then we look at its child, and then we decide that which of the recursion formula will be applicable. And then we use one of the values of the table corresponding to the child. So in this case, we are interested in computing this entry. This is our node x2, and the S subset is c comma h. So first thing is to decide what kind of node it is. So we look at its child. So this child is having h, and this is having c comma h. So that means c is introduced here. So that is why this is an introduced node. So we'll use the recursion formula corresponding to an introduced node. So what is the value of S? S is c comma h. Now, what is the introduced node? C. So is C belonging to C comma H? Yes. So this is the rule that will be applicable. So what does this rule say? This rule says that you add 1 to the entry corresponding to the child x dash. So here the child of x2 is x3, and it has two table entries. One is corresponding to phi and another is corresponding to h. So which one shall we take? So S is already CH minus H. So we should take the one corresponding to, sorry, S is already CH minus V. The introduced node is C. So CH minus C is H. So therefore we will take this entry x3 comma H, the entry corresponding to x3 comma H, and this is 1. So this is saying that among these vertices there is an independent set of size 1 that satisfies the properties that we want to be satisfied. So now it is already 1. So 1 plus 1 is 2. So that is how we computed the entry corresponding to x2 and c comma h to be 2. So do you understand? Or is there any here introduced vertex is C, exactly. So H is the vertex which was already there in the child. So we are looking from child to parent. So in the parent, in X2, we came across C. So introduced vertex is C. X dash is a child node, yes. So we look at the child node and we are doing a bottom up processing. So we are moving from child to parent. So when this computation was going on, the computation direction was from X3 to X2. And the definition of an introduced node is that there is one vertex in the introduced node which is extra when compared to the child vertex. So what is that vertex which is extra when compared to the child vertex? Extra vertex is what in X2? So are you convinced that the extra vertex is actually C? Okay, you got the point. Good. Fine. So now we have already seen an example of an introduced node. Now let's move to the next one. So the next one is also an introduced node. So X1 is an introduced node because it has one vertex extra when compared to its child. Okay, so we're interested in computing this entry. So this is saying, oh sorry, this is already 2. We are interested in what? We are interested in computing X1 E comma H. Okay, so X1 is introduce type of node because it introduces E. So other than its other so the content of the bag corresponding to its child is C comma H. So in this node there is an additional vertex E. So E has been introduced in this. So now we apply the same formula. So now E is part of E comma H, right? So shall we apply this or this?
Second one.
Yes, because he is part of E comma H. So now the question is after we remove, okay, so minus infinity thing, so let's just look at it once. So when does an entry correspond to minus infinity? If we are unable to find an independent set that respects all the properties that we want. Okay, so so okay, let's go by the second formula corresponding to the second one first. So S is what? S is E comma H. Let me write down. And just remove these things. So in this case, S is E comma H. So S minus introduced vertex is E. So S minus V is H. We're interested in this entry. Yes. So what is the entry corresponding to X2H? X2H and H is 1. But even before going there, we have to check. Now we have to check the definition. So what is the definition? Definition is saying that you give me that maximum independent set whose intersection with the bag is S. Okay. So what is S? S is already EH. Now you have to take EH. Other than EH, you can take other things. Okay. So the matter is, so is it possible to have an independent set where both E and H are there? See, E and H is part of an H. So there cannot be an independent set that contains H and E both. Okay. So therefore, what the definition is asking So that definition can never be satisfied. That you give me that independent set which contains E and H plus maybe additionally something which you know uh, follows, I mean, satisfies these properties. So therefore, we cannot find such an independent set because EH itself is an edge. So therefore, we will apply this, non-existence rule, which says that such a situation, in such a situation, we set the value to minus infinity. So this one is actually minus infinity.
So I think that some modification can be made in this rule, like say, can you please scroll it down a little bit so that yeah, this rule scroll down please so that I can see that formula which you wrote for recursive formula which you wrote for this node. Yes, so here we can write that if V is the element of S, then the first thing is applicable. And if V is not the element of the S, then the first rule. And if V is the element of S and the V of X intersect V of X, I mean, if intersection of V of X and S excluding V is equal to phi, then this value would be infinite.
Correct. Right. So I just wrote this rule. I just reproduced this rule. So maybe it is not as formal as it should be. And but the formal rule is in the book as well as in the video. So what you said is correct. So whenever we have a situation, so first thing we check that whether there is a feasible solution or not, which respects the definition. And if the definition is respected, then only we apply the rule corresponding to the child node. Like we look up the table corresponding to the child node. So the table lookup will only happen if uh, the subset S, they themselves are not part of edges. Correct. So here
Yes,
EH itself is an edge. Now both the vertices of the edge cannot be part of the independent set by definition. So therefore, there is no
yes,
way the definition can be satisfied. So all formal, you know, description of the recursion rule are in the book as well as in the lecture videos. But here the idea is to just walk you through the solution of the problem.
yes, yes, yes,
But I agree with you that there is
yes.
scope for making it more formal. So this one is minus infinity. Now we are looking at y25. So y25 is where y2 is this node, and we do not know this value. So we are asking the question that give me an independent set in this subtree where there is no restriction of what you will take because this is phi, but you want that the independent set is of maximum size. The first thing is what is V of y2? V of y2 is EFH. So EFH itself is a triangle. So from a triangle, how many vertices can you take in the independent set?
Phi.
From this triangle, you can take one vertex that is always independent. One of the vertices you can take. See,
But
E and H you have to have.
but definition of independent set says that the vertices which are independent of one another. None of the vertex is connected to any other vertex in that set.
Exactly,
That will be called the independent set. So
exactly.
if I take even one vertex f, so that is connected to two vertices here, h and g. So even individually f will not make an independent set, is it?
No, so when you say that, suppose you are given a graph. The graph has 1,000, 1 lakh, 1 million vertices. You don't care. So if you are saying that I am taking one vertex and I declare that this one vertex is an independent set, then is that correct or not?
Yeah, so in that set, since no other vertex is there, so the question of connectivity doesn't arise.
No,
So
no. So
therefore, this
there is an no. I am no. Let me make it more precise. So suppose you have 100 vertices, each of them connected to every other. Every vertex is connected to every other vertex. 100 vertices. Okay, so this is a
Yes.
complete graph in 100 vertices. So I am saying that you report one vertex as an independent set. Is that correct or not?
Yes, that's correct. That's correct. I agree with you. So for a complete graph having any number of the vertices, the maximum independent set of any complete graph would be equals to one. Is this correct?
Yes, yes. So in a triangle, what is the independent set size? In a triangle, in three vertices. So triangle is nothing but a complete graph in three vertices.
Yes. So its value is equal to one.
Yes. So what does this definition? So I am just going by the definition, but of course we should not do it this way. So intuitively we can look at it and we can find an answer. So this is a shortcut that okay, this is asking me my25 is asking me that what is the independent set composed of vertices E, F, and H, and E and H you do not take. No, so E and H you can take because this thing is 5. What is the maximum? So basically, what is the maximum size independent set composed of E, F, and H? So basically, you have a triangle, so you can take at least, I mean, at most one. So that is the reason this is going to be one. I can see immediately, but we have to. I will just now write what is the recursion rule for a forget node. So this is a okay. So first thing is this is a forget node because in the child there is a vertex which is missing in this, and that vertex is F. So in this node Y2, the forgotten vertex is F. So let me write down the recursion rule for the forget node. So I'll just push this down. It is a one-liner, so it will not take much space. Okay, it's hard to push these things. Okay, actually, I'm not able to push this. Okay, this worked. So the recursion rule, which is in the book, in the description of the algorithm, is the following. So for a forget node, where B is the forgotten node, forgotten vertex, I should say, the table entry corresponding to x comma s is nothing but max of the table entry corresponding to the child t dash, I mean make it x dash is the child of x, okay? So x dash comma s and the table entry corresponding to x dash comma s union the forgotten node. This is the recursion rule. So now we are looking at this vertex, this node, the forgotten node here, p is equal to f. So you are interested in the child node of this. So y3 comma phi and y3 comma f. So y3 comma phi is 0 and y3 comma f is 1. So this is plus 1. Do you understand what I said?
Yes.
So this one is plus 1. So this is plus 1 minus infinity to this is possible. This is also possible. This is also possible. So Shivang, are you okay with the calculation of this node? Okay. So now we can move to the okay, it is already about 7:30, so we'll slightly speed up. So y1e. So y1 is where? Y1 is here. Y1 comma E. So we are interested in this one. So what kind of node is y1?
Forgotten node. C is being forgotten here.
So y1 is the node which has one extra vertex than the child. And by definition, if there is one extra vertex, so something is getting introduced and not forgotten. So y1 will be an introduced node. Isn't that true?
Introduced. Yes, sorry, introduced node. Yeah.
Yes. That's fine. So okay, so I will leave it to you to maybe I will give you 2-3 minutes so that you can give me the answer. Oh, the rule is not visible to you, so I'll just do one thing. I'll push this thing slightly up so that both the rules are visible. Okay, so this is the rule for the introduce node. And now I think, yeah, I think it is visible. It is visible, I believe. We're interested in this node, y1. This is an introduced node. The introduced vertex is C. So we are interested in computing y1 comma E.
Yes. So its value is 1.
Correct. That is correct. So I'll just go through quickly why is it 1? So the introduced vertex is C, and C is not part of the set E. So this rule will be applicable. So look at the child node and the same subset. The child node is this, the subset is E. So y2 is 1. Therefore, this one is going to be 1. Is that correct? Did you also reason similarly? Was the reasoning same or you had a different reasoning?
Uh, so can you repeat your question? You were not audible for a while. Yeah.
Yeah, so I just explained how I came to the conclusion that this is 1. So did you also have the same reasoning or you had a
Yes.
different?
Yes.
Okay.
Same reasoning. Following this formula, and since E is the element which is C is the element which is being introduced, and that is not the part of the set S. So first rule is applicable, and therefore
Yes,
resulting into this value. Yeah.
exactly. Okay. So now we'll move to the last one. The last one is basically corresponding to the root. So we do not know. So this is a join node. So we are interested in computing this entry. So we're interested in computing this entry. It is a join node. So I will write down the rule for the join node first. So the join node rule I'll write down here because other places are not visible. Just push this thing to the top. Okay, so here is the recursion rule for the join node. Just look it up from the book. So for a join node, they are saying that the m of table entry m x comma s is equal to the table entry m, the first child. Let us say first child is x1. So let us say, yeah, here, yeah, fine. Okay, I'll just write it r. So table entry corresponding to m r comma s is the first child is x1, the second child is y1. So table entry corresponding to x1 comma s plus table entry corresponding to y1 comma s minus uh, ws. Okay, so WS, so this is the weighted setting. So here, just a second. This is WS. So here, okay, so WS means okay, fine. So W mod S, I'll just say mod S. So wait, okay, so how many elements are there in S? Okay, so this is the formula. Okay, so now we can do the calculation. So S is what? C, and everything is there in the all the vertices are there in the rooted subtree at R.
What is to be computed?
We want to compute this entry M R comma C.
Okay, MR. See.
Yes. So here the value of S is nothing but the singleton set SC, and we are looking at these two children. So what is x1 comma C? X1 comma C is 2, and what is y1 comma C? That is also 2, minus what is the cardinality of C? That is 1. So that comes out to 2 plus 2 minus 1. So that's 3.
Yes.
So we have computed all these values, and the correct answer is mm, so whichever is the correct answer.
Second option is correct in entirety. Out of
Okay.
these four, yeah.
Okay. So the point is, at the end, we look at the entry corresponding to uh, the root, and here we have seen that there is a independent set of size 3. Finally, we can see that even in the original graph, there should be an independent set. Yes, A, F, and C is an independent set. This is having size 3. 3 vertices are independent of each other. Fine. So this is a long question. I think there would be some questions of this sort in the present assignment. Okay, so this is the second. Oh, so what is the second question? Uh,
So,
uh,
how to find this tree decomposition? What is the process of getting such a nice tree decomposition?
right. So we'll look at one of them. So since you asked, so let's look at this question. Okay, so that one was not three. So this is question 2. So since you asked how to find a nice tree decomposition, so let's look at the third question before looking at the second question. So this is relating to that. So I'll let you read the question for a minute.
Slightly scroll it down, but just thanks. That's okay.
So here it is saying that uh, you have a graph and the corresponding depth first search tree is given to you. And there is one video which has been referred. So from this DFS tree, there is a way to find a tree decomposition of G of width at most 3, and width is at most 3 because if you look at the back edges, that is the edges which are just use the pen, which are sort of dotted. These dotted edges are moving from one level to their you know ancestors, so they're not jumping at more than 3 levels. So this is not exactly the question that you're asking. So you're asking how one can find a nice tree decomposition. This is just giving an example of how one can find a tree decomposition using the DFS tree. To answer your question, how we can find a nice tree decomposition, let me just look at it once. I'll just try to look it up. How to find There must be. Okay, so there is a theorem that says that if you have a tree decomposition of width k, uh, just let me. I read this theorem, but just let me find it out. It is in the seventh chapter. Uh, Number four, I think.
So which book are you referring to? That parameterized algorithm book?
Yes, yes, yes. That book.
Okay.
Right. So lemma 7.4 that says that if a graph admits a tree decomposition of width at most k. So there are ways in the book, if you see in the seventh chapter, there are ways in which a tree decomposition can be computed approximately. That means not optimally, maybe slightly off from the minimum width. But if you find that tree decomposition approximately, from the tree decomposition, there is a way to get a nice tree decomposition of width at most k. That means of the same width of the tree decomposition, and that can be accomplished in reasonable time. Order k square max of the vertex set size of the tree, comma the vertex set size of the original graph. So there is an efficient way to compute a nice tree decomposition from a tree decomposition without losing the width, without losing anything on the width.
Okay. Okay. And why are we so much interested in getting a nice tree decomposition despite having the tree decomposition, normal tree decomposition in our hand?
Because if you have nice tree decomposition, then these kind of dynamic programming techniques can be applied. For example, because we had nice tree decomposition, we could say that to find the table entry for a particular bag, you just need to look at the table entry corresponding to its child. The child is either having the same identical bag as the parent or one more or one less vertex. And that is the reason uh, we are able to say all these nice things and construct tables quickly and find solutions to problems like weighted independent set, dominating set, and many other examples are there in the seventh chapter.
Okay, okay, yes, yes. So yeah, so otherwise the to get a tree decomposition might be a computationally intractable. If not computationally intractable, then at least a difficult problem to solve to decompose a graph into a tree. And since that tree is difficult to compute, so probably people might have invented this DP based technique with some modifications so that this is easy to compute. Is this the case?
Yes, so there are some graphs for which the tree width is bounded. That means the tree width is some constant k. And because the tree width is bounded, therefore even if you have a running time of 2 to the power k, there is a graph G whose tree width is at most k. Let us say k is a constant. Okay. Then even if you have a running time of 2 to the power k and to the power constant, that is okay. You are still in the polynomial running time domain because k is a constant. But there are graphs for which tree width is not bounded. One example is kn. So the tree width of the complete graph is n minus 1. For such a graph, if you have this kind of a running time, so that is already 2 to the power n minus 1 n to the power constant.
Yes, yes,
So
yes.
that is exponential.
Mhm.
So therefore, for those graphs where the tree width is bounded, there if we say something, if we say some running time in terms of the tree width, then we are basically saying something interesting.
Yes, yes. And even though I could not find, but what could be the? I mean, why do we study such kind of the tree decompositions? For what purpose? I mean, what do we want to decompose a graph into a tree in this specific form?
So the primary motivation is to design dynamic programming algorithms. And whenever you have a tree, the beauty of the tree is that, so consider any tree. Look at this tree we are currently looking at. So this is a tree. If you
Mhm.
delete one vertex, then the tree is disconnected. So it is disconnected into two components. Suppose I delete two, then there's one component which is this, and there is another component which is this. Okay. So now, if you solve something in these two components, then you say that okay, we will merge the solution corresponding to this component and the solution corresponding to this component, and then you can say something about the solution for the entire tree.
Yes, yes,
So
yes.
having a tree lets you divide the problem into sub problems because there is a vertex which is acting as a separator. Every vertex is acting as a separator.
Mhm.
So
Yes,
the more a graph resembles a tree, that means we are so basically the idea of Treewidth is to uh, informally express the graph in a tree-like form. And once we have that tree-like form, then we can say that okay, the separator size is probably not too large. So that means there is a set of vertices. If you do delete those set of vertices, then the graph becomes disconnected. And then in the different connected components into which the graph gets disconnected, you can apply your algorithm, divide and conquer or dynamic programming type of algorithms.
okay. And what is the rationale behind this idea of bag?
What is the rationale behind this idea of bag? So, okay, so you're saying that why the bags are defined in this way that for every edge, you need a bag having both the endpoints, and for every vertex, all the bags should be connected.
Yes,
So
yes,
you're asking why uh, the way tree decomposition is defined, what is the rationale behind the definition?
yes. Uh, because the idea, because the concept of introducing a tree is very much clear from your explanation. That we can handle the situation and we can come up with solutions bit easily because of this separator thing. But how to construct a tree in this specific form only, that the connectivity among the bags should be maintained if one element, I mean, if one element is appearing in the multiple bags, then the connectivity among those vertices should be maintained. And
Okay, so what is the algorithm? So I do not know whether the definition is the definition is inspired by algorithmic applications or the definition is standalone. It is more combinatorial. That is not known to me. Uh, but this is definitely a good question, and I will answer that question. Try to answer that question next time.
yeah,
But
yeah, sure, sure, sure.
so this example itself. So the thing is, there are certain graphs for which if you, for example, in this case, uh, this is a graph and this is the DFS tree. So in the DFS tree, the number of vertices is exactly equal to the number of vertices of the graph. Okay, and it is possible that we will see that it is possible to have a tree decomposition of this graph. Tree decomposition means decomposition respecting those two properties, the way they define tree width, such that even in the tree decomposition, the number of vertices will be exactly same. So there are some motivations I do not know. So let's do one thing. Let's look at this example first.
Yes, yes. But only 10 minutes are remaining. So would we able to?
Yeah, this is
Oh,
a simple one. This is
okay,
simple
okay.
one. So this is just showing. This is an example. It is a very nice example. This is showing that once you find the DFS tree, the depth first search tree for this graph, then there is a very simple way in which you can also find a tree decomposition. And in the tree decomposition, the tree width is bounded by 3. And why 3? Because in this DFS tree, the back edges are not having large jumps. Jump in the sense, so when I say that jump, so 4 is having a back edge to 1. So there's a jump of 3 vertices.
So package means
Package means just a normal package. So let me go through how the DFS tree is constructed. So this is the graph, and let us say that what is the question? Note that the endpoints of every package differ by at most three levels in the DFS tree. And the question is to find the tree decomposition of G of which atmosphere. So the DFS tree has to start somewhere. So that is the root. So it is starting at one. So see, the DFS tree is not unique. So you can have many different DFS trees. So starting at one, so one is having neighbors. So one is neighbor two, two, 6, and 3. So you first go to 2. Okay. So from 2, you can go to either 4 or 3. So here it is going to 3. So it has gone to 3. So from 3, you have two choices, 4 and 5. So you go to 4. But if you go to 4, then 4 is again neighbors to 1 and 2. But 1 and 2 are already visited. So that is why you have a package. So this is a normal uh, DFS traversal algorithm. So you start with the vertex and you look at multiple neighbors. So you go to one of the neighbors. In this case, they are going to 2. So from 2, again, there are options. So it goes to one of the neighbors. From 2, it is going to 3. From 3, it is going to 4. But once it is at 4, then it realizes that the two edges that are still to be explored are going to already visited nodes. That is why there are back edges. Is that clear, or you want
yes,
any?
it's clear. The construction of the DFS is clear. And what I understood that once the construction of the DFS tree is over, and since in the original graph we do have an age in between 4 to 1, and which has not been considered in this DFS tree, so this can be considered as a package.
Correct.
So, so here we have it is given that the every package differ by at most three levels. So what this how this three is appearing here?
So it's just this. So from 4, there is a
Yes,
back edge to 1. So what is the level of the root? So level of root is level 0. What is the level of its child? So this is level
okay,
1. What is the level
yes,
of 3? This is level 2. What is the level of 4? This is level 3. So there is a package from level 3 to level 0.
yes. So probably it is the maximum number of the edges traversed in between to reach to one. So this value comes out to be one, two, and then three. So yeah, correct. Your
Definitely,
video got
they're
freezed.
saying that.
Yes, your
Oh,
video got freezed. Okay, audible now. Audible now.
there is probably some problem. Come to the department. Uh, so
Yes, so it's clear that this differs by at most three levels. Yeah.
correct. So once you have the DFS tree, it is very interesting that from this DFS tree, you can get a tree decomposition of very small width only 3. So that is the question, that how do you get that? So I'll just give you the rule. So the rule is the following. So you follow this rule, will move slightly up. So if at any point you're not able to see the two diagrams, the graph as well as the tree, then you let me know. So you do it this way. So the way to draw a tree decomposition is to draw each back X and its ancestors. Okay. Ancestors in the sense three ancestors. So I'll just quickly draw What I mean is that, so you start with this. So you're looking at the DFS tree. I hope the DFS tree is visible. So the root is one. So you have a pack corresponding to one. So one's ancestor is nobody. So one itself is a root. Now you have two. Two's ancestor is one. So two one is a bag. You have six. Six ancestor is one. Six one is a bag. You have seven. Seven's ancestor is a bag. So you have, actually I should say two comma one, but I'm just saying two one. Six one means six comma one. So these are in the back. So now three is there. Three's ancestor is two one. And six has no descendants. Again, we have this. So four's ancestor is three two one. This is like this. Five's ancestor is three two one. So this one is another thing. So eight's ancestor is seven and one. 12's ancestor is seven and one. So are you getting what I'm doing?
Yes, it's clear. So you are
Right.
moving
So
three
nine,
steps. Yeah,
yes,
9871 and
11,
11
8.
8 7 1.
What else we have left with? We need 10. So let's take 10. And from these, there are four ancestors. So 10 has four ancestors. I'll only take three, and that will be sufficient. So we want to minimize the size of the bag. Oh, sorry, 8, 9, 10, 8, 9, 7, 8, 9, 8, 7. So this, my claim is that this is a valid tree decomposition. So this is, so let us first verify whether this is correct or not. So because for every edge, so so for every vertex we have looked at its parent. So for every edge there is definitely a bag containing the endpoints of that edge. That is
Yes.
clear. Now for every internal node, we have looked at the ancestors of that internal node and taken three of them. So for example, let us say 7. So 7 is counted in this node, that is 7, and then this node, that is 7 and its child and parent. That means, so you understand, all the ancestors and uh, descendants are sort of connected because of this
Your video got freezed, and uh, even your audio uh, is not audible. You were not audible for a while.
Okay, so I think that there is some network issue right now. Okay, sound quality is bad.
But I could hear till this point that this is a valid tree decomposition, and then you explained that so all the edges have been covered, and moreover there is connectivity in between these bags. Uh, uh, because yes, so that is well understood. So what I perceive from here, that if the DFS tree is ready, then from the DFS we can construct a valid tree decomposition. So from the DFS tree, we identify the maximum level of the packages, and then we can construct the valid tree decomposition.
Yes, so this actually says that I think I'm audible, better audible now. So
Yes, yes.
this actually says that there is a relationship between the jump.
Again, your video got freezed, and you are not audible. If you can hear me. Your video is freezed.
Of DFS. Okay, so I think it's already time. So let us conclude for today. There is some network issue anyway.
Yeah, sure.
So I thank both of you for joining.
Thank you so much, and
Let's meet.
please upload notes and the video. If video is if there is some network issue, then at least upload notes, because notes are really helpful to revise what we discussed in the previous sessions.
Yes, yes, I'll do that. Thank you.
Yeah, thank you so very much. Yeah, good night.
All right. Good night. Thank you.
Bye.